Today we're going to be continuing with Chapter 4, looking specifically at the second derivative and how that affects the graph. Okay, so we talked a little bit in the last section about concavity, and so concavity has to do with the way the graph is actually kind of cupped. So if you look here, like you can see that this is more or less like it's holding water, it's kind of cupped upward. Here it switches and it starts being kind of a downward cup. And then over here, you've got, it turns back to kind of cupped upward or a concave up. And I always think of it like if you were to put water in it, concave up, the water is going to stay in. Concave down, it's going to run out. Okay. So that's kind of what you're looking at. And so there's always a place where it divides and changes from being concave up, where it's holding water, to concave down, where the water is going to like pour out of it. So that is kind of what you're looking at with that. So these places it changes are called its inflection points. So we're going to look at mathematically how to find those, but just visually you need to understand that it's where it changes from being concave up to concave down, or concave down to concave up are called inflection points. So it's not like maximums and minimums where they're different, like one's a peak and one's a valley. One's going from positive to negative and one from negative to positive. Here, as long as it changes, is called an inflection point. It can change in either direction. Okay, so you can have two different types of graphs. So we know that two different types of graphs that are increasing. We know that from chapter 1, or section 1, I should say, that the first derivative tells us whether the function's increasing or decreasing. So if your first derivative is positive, the original function is increasing. But it can increase in two different ways. It can increase concave up, because here we're rising as we go from left to right, but this is kind of cupped upward. This is still increasing because it's rising from left to right, but it's cupped downward. So what happens with this is it's increasing, but it increases at a faster rate the further it goes, okay? So it starts out, if you think about the tangent line here, and then the slope of the tangent line here, and then even up here, if I can draw it in, you can see that that slope gets steeper and steeper. So when that happens, you get a concave up type graph, which means it's accelerating. So acceleration actually comes from the second derivative. Here, like we said, this one is still increasing, but if we consider the slope at different points along the way, you can see that that slope is getting less and less. It's flattening out. So while it is still increasing, it's increasing at a slower rate. Therefore, it's a deceleration. Same thing with decreasing. We can decrease in two different ways. So we can decrease concave up. In that case, it's decreasing, but it's decreasing at a slower rate. So you kind of see this leveling off that's occurring here. Over here, it would be decreasing concave down because it's cupped downward. And so you would be decreasing, but decreasing at a faster rate, because you can see here it's more level, here it's getting steeper and steeper. Okay, so both of these are examples of increasing functions with different concavities. So this one is increasing concave up. This one would be increasing concave down. Okay, if we look at this from Desmos, what we see is I can move this point around the graph, and it's drawing the tangent line in at each place. So let's go back over to the beginning part here. We can see that this first part this part here is concave up to its inflection point. And if you notice for all of that, what's going to happen is the graph is going to be above the tangent line. So when I move this point to different places, the graph stays above the tangent line. Okay, so the graph is always above that tangent line until I pass that inflection point. When I pass that inflection point, now the graph is actually, it's a little hard to see there, but the graph is actually below the tangent line when it's concave down. So all these points along the way here, you can see that the graph is below that tangent line when it's concave down. And then again, when it passes the inflection point over here, it's going to switch and the graph's going to be above the tangent line. So anytime the graph is above the tangent line, it's concave up. Anytime the graph is below the tangent line, it's going to be concave down. Okay, and that's what I just kind of what I was saying there. Okay, so there are definitions of concavity. The graph of a function f is concave upward on the interval if the first derivative is increasing, okay? Or another way to think of that is that the second derivative is positive, okay? Here, the graph of the function f is concave down on the interval if the first derivative is decreasing, or in other words, the second derivative is negative. Okay, so we can talk about this second derivative that I mentioned here. And the good thing is second derivative is not new formulas. It's just simply the derivative of the first derivative. So notationally, we've got the two little prime signs. So f double prime is what we say of x is equal to the derivative of f prime of x. And you can see it written like this as well. We probably won't use this notation all that often. Okay, so I made this chart here to kind of summarize the relationships here. So if we're talking about the second derivative, okay, the second derivative, if it's positive, then what that tells us is that the original function is concave up, and if the second derivative is negative, the original function is concave down. Okay, so if we look at just simply finding the second derivative, our second derivative here, we've got x to the third is our function. So the first derivative, of course, would be 3x squared. And then the second derivative is just the derivative of this first derivative. So that would be 2 times 3 would be 6x. Okay, as far as graphing the function, what we want to do is we're going to consider our first derivative. We said that was 3x squared. And we said our second derivative is 6x, okay? So if we do two sign charts, the first one is going to be for our first derivative, and then the second one was going to be for our second derivative, because they tell us two different things, okay? We want to first of all find the critical numbers for each derivative, okay? So for the first derivative, if I'm finding my critical numbers, I'm just going to set that equal to 0. So I'm going to get x is 0. So that's going to be the number that goes here. And then I'm going to set the second derivative equal to 0. So I find in this particular one that my critical numbers for both are 0. Okay. So what I want to do when I analyze this is if I'm looking for the first derivative, for like how the first derivative behaves, then of course I want to plug into that first derivative. So if I put a positive number, something greater than 0 in, like maybe 1, that would be 1 squared times 3, so that's positive. If I put maybe negative 1 in, 3 times negative 1 squared, if we square that negative 1, that would be a positive, so this is going to be a positive. So what that tells me is the original function is increasing and then also increasing. So it's increasing for all of the values. If I look over here at the second derivative, again, we've got the same critical number, which is just coincidence, doesn't have to happen that they have the same number as the critical number. I'm going to go and I'm going to put in a positive number this time, something more than 0, but I'm looking at the second derivative, so I'm going to put it into this. So if I put 1 into that, I get a positive, and if I put, say, negative 1 in, 6 times negative 1, I get a negative. So what that tells me is the second derivative doesn't tell me whether it's increasing or decreasing. It tells me whether it's concave up or concave down. So this part means it's going to be concave up, and this part is going to be concave down. Okay, so we've got this graph here, and we have 0 as our critical number. So for the positive part of our graph, it is both increasing and concave up. So it's going to look something like this. That would be increasing and concave up. The left side of our graph, or the negative part of our graph, it's still increasing, but this one's concave down. So it's going to look something like this. Okay, so we've got increasing concave down, increasing concave up. Okay, and it's kind of hard to see, but you can see the calculator graph here, and it looks like what we came up with as far as the key characteristics. Okay, let's take a look at this next example here. So we want to find both the first and the second derivatives for this, and I'm going to back up a little bit here. So the first thing on one like this is to, we've already talked about, rewrite it so you can take your derivative. So the first derivative then, you're just going to bring that 1/2 down in front, or 1/3, excuse me, 1/3 down in front, recopy the x, subtract 1 from the exponent, so -2/3. So we've got 1 over 3x to the 2/3. And then for the second derivative, it's going to be easier if we go back to this form of the first derivative. So we're going to have 1/3, that's our constant multiple. We're going to bring that -2/3 down in front, subtract 1 from our exponent, and that's going to give us our second derivative. So we'll have -2 over 9x to the 5/3. Okay, so if we want to, again, come up with our graph for these, what we're going to have to do is set these equal to 0 and solve for our critical numbers. So we'll have okay, so there's actually nowhere that this equals 0. But if you remember with your critical numbers, you also can have a critical number where it's undefined. So this is actually going to be undefined. Okay, so it's undefined when x equals 0, because that would give me 0 in the denominator. So that would be the first derivative is undefined when x equals 0. The second derivative is also undefined at 0. So 0 again would both be a critical number for the first derivative and also for the second derivative. And I have seen people combine these two graphs together into one chart that shows the original function, the first and the second derivatives. I like to keep them separate, but it's kind of personal preference. Okay, if I put in a number, we'll check in the first derivative, which means we're substituting in here for the first derivative. If I put like 1 in, that would give me a positive, and you can verify that if you want to. If I put a negative in, that's also going to give me a positive. So let's say I put -1 in, and you can verify that if you need to. It's going to give me a positive. So that means it's going to be increasing and then increasing again. For the second derivative, if I put in a like 1, this is going to be a negative here. And you can double check me on this again, but if you put a -1 in here, you are going to actually end up with a negative divided by a negative, so you're going to have a positive. So what that means is this part would be concave up, and this part is going to be concave down. Okay, so let's look and see what the graph looks like for this. Okay. This is what the actual graph looks like. So we had said that it's actually increasing for the whole graph. So we see that that is in fact increasing for the whole graph. Here at 0 was our critical number, so that's where it kind of changes, could potentially change concavity. And so it does go from having a positive second derivative, which means it's concave up, having a negative second derivative, which means it's okay. And this just kind of summarizes it, what we've talked about. certainly some good examples for us to look at. Okay, on this one, we're asked to find the intervals where it's concave up and concave down. So that means we're going to be working with our second derivative. So we first need to take the first derivative. So the derivative of e to the x is, in fact, e to the x. And then the second derivative, the derivative of the first derivative, is also e to the x. So our derivatives are pretty easy, okay? The next thing we want to do is we want to figure out where we have critical numbers. So we want to set e to the x equal to 0. Okay. All right, so that means we need to solve this little mini equation here and see if we get any answers. So if I take the natural log of both sides, hopefully you remember that we cannot take the natural log of 0, so we don't really get answers from these. So what that tells me is that it's not changing anywhere. So we have no critical numbers. There's no place this is undefined. There's no place where it equals 0. So we don't have a change of anything. It always either stays increasing or decreasing, and it always stays either concave up or concave down. So we don't really have numbers to put on this sign chart. We can still do the sign chart though, we just don't have a specific number to divide this. So I'm just going to pick any number, and I'm going to pick the easiest number, which is 0. So if I plug 0 in, I get e to the 0, which is 1, and that's positive. So if I have a positive first derivative, that means my function is always increasing. And then if I do the same thing for my second derivative, okay. So again, I don't have any critical numbers to divide it, so it's either always concave up or always concave down. So by the same rationale, if I try 0, I end up with a positive. So it's always concave up. So the graph of e to the x is concave up for all real numbers. So it's concave up for all real numbers, and it is also increasing for all real numbers. So there's not a lot interesting going on for that particular example. Okay, I'm going to skip over this one. And we're going to talk a little bit about finding inflection points. So we mentioned these at the beginning. An inflection point is a point on the graph of a function where the function is continuous and the concavity changes. And it doesn't matter which way it changes. It could go upward to downward or downward to upward, and they're both inflection points. So it just requires a sign change of the second derivative. All right, so the first thing in finding our inflection points is we want to find all of our partition numbers, or basically we've been calling those our critical numbers of the second derivative. So a very similar process to what we used in finding maximums and minimums, except we did that for the first derivative. And so we're going to take that same process and do it for the second derivative, and it's going to give us our inflection points. So we're going to find our critical numbers, construct a sign chart of the second derivative, and then if we see a sign change, then that's going to indicate we have an inflection point. Okay, so let's get to work on this one. We know when we talk about inflection points, we need to look at our second derivative, okay? So we've got to start out and find our first derivative. So the first derivative here is going to be 12x squared plus 12x minus 72. Okay, and hopefully that's easy for you now. We need the second derivative because this would give me maximums and minimums if I set it equal to 0. This is going to give me inflection points. So here my derivative is going to be 24x, and here it's going to be 12, and then that's going to be 0. So if I set this equal to 0 and solve, divide by 24, so x is going to be negative 1/2. So that is my critical number to put on my sign chart, negative 1/2. So I want to look at my second derivative to see if I can find out if this is in fact an inflection point. Okay, so I want to, whatever's here, that's where I want to plug it into. So if I pick a test point of maybe 0, because 0 is more than negative 1/2, If I put 0 into the second derivative, I'm going to get a positive. That would be 0 plus 12 will be 0, would be 12, which is positive. If I put, say, negative 1 in, because that's less than negative 1/2, that would be 24 times negative 1 plus 12 is going to give me a negative. So we have this part being concave down and this part being concave up. So since we do in fact have a sign change here, that means this is an inflection point. Okay, and generally it's going to ask for both the x and the y coordinate. So we'll have negative 1/2 for the x coordinate, and then I need to plug in negative 1/2 into the original function because all points come from the original function itself. So if I plug negative 1/2 in here, I'm going to get 7. And you can double check that. Just plug negative 1/2 in. Be careful about your signs. And we get this as our inflection point. You do need to show this. You can't just, like a lot of people will do this part and automatically give me the point and say they found the inflection point. It's not technically an inflection point until you show me that you have this sign change here. And you can see on the graph that here, this is the point that we found, and clearly that is the place where it changes from being concave down to concave up. All right, we've got one. If you'd like to try it on your own, feel free to do that. We're asked to find the inflection points again, which means we're going to repeat what we just did. We're going to take our first derivative, and then we're going to take our second derivative. So just keep going. We could do third derivatives, fourth derivatives. We can keep going as far as we want to with this. Okay. All right, so we need to find the critical numbers. This is a polynomial, so we don't have to worry about undefined places. We just need to figure out where the derivative is equal to 0. So I'll move that 18 over and it'll become positive. Divide by the 6. So x is 3. Okay, so we need to do our sign chart. Remember, that's a part of the verification process to in fact show that it is an inflection point. Okay, so we're going to pick a number more than 3, so we'll say 4 as our test point. So 6 times 4 minus 18 will be positive. If I pick something less than 3, like maybe 1, 6 times 1 minus 18 is negative. So this is going to be concave down, and this is going to be concave up. Okay, so we do have this sign change going from concave down to concave up. So that means this is an inflection point. So our point is going to be 3, and then we have to plug 3 into the original function. So back up here, and when I plug that in, and again, verify this yourself, is going to be 8. So 3, 8 is the inflection point. Okay, so looking at this graph here, we're asked to find the characteristics of the original function f given this derivative graph. So when we look at this, I'm going to write down some key characteristics here. And looking at this, we know that the derivative at -1 is equal to 0. Okay, so we've got that here. We also know that f of 1 is a maximum of that first derivative. And then we also know that f prime of 2 is equal to 0. So our first derivative is positive. It's positive here, and then it goes negative. So if we're looking at a sign chart, I think that's the easiest way to consider this. We're wanting to figure out, kind of working backwards. Before we use the first, we want to fill in from the characteristics of the first derivative, we want to fill in what we know about the function, the original function itself. So we always put on our number line the places where the first derivative equals 0. That's our critical numbers. So since this is the graph of the first derivative, The places it equals 0 is here and here. So that's going to be our critical numbers. -1 and 2 are the critical numbers for the first derivative. Okay. So when I look at this, the numbers, anything less than -1, our first derivative is positive. Between -1 and 2, it's also still positive. And then it goes from positive to negative, okay, because it goes below the x-axis here. Okay. So that tells me that my original function must have been increasing here, and then decreasing for this part. So I could say that we know the original function was increasing from negative infinity to -1, and also from -1 to 2. And we could also say that it's decreasing because it's negative here. We have a negative first derivative. It's decreasing from 2 to infinity. We don't have a sign change here, so our original function would not have had a maximum or a minimum, for no local extrema here. But we do go from positive to negative, so that means at x equals 2, we would have had a local maximum. Since it went from positive increasing to negative decreasing, we'd have to have a maximum that's occurring there. Okay, so we've talked about the first derivative. Let's look at the second derivative and what we can see from that. So on our second derivative, okay, the second derivative, we've got our maximums and our minimums are actually our critical numbers here. So we're going to have -1 and +1. Those are the places that our second derivative is represented not by whether this is above or below the x-axis, but instead whether it's increasing or whether the first derivative is increasing or decreasing. So for this one, we have, because when we're looking at the second derivative, we're looking at something different. Okay, so we have our critical numbers here at -1 and here at +1. So this part of our graph is decreasing. This part is increasing, and this part is, in fact, decreasing again. So when that happens, what that means is if our first derivative is decreasing, that means our second derivative is negative. Here, our first derivative is increasing, so that means our second derivative is positive, and then this part here, since our first derivative is decreasing, our second derivative is negative. So what that tells me is that we have concave down, this will be concave up, and then this will be down again. So because we do have sign changes, we actually have two inflection points. So we have an inflection point at x equals -1 and also at x equals +1. And so what happens is if you're looking at that first derivative, the inflection points are actually the maximums and minimums of the first derivative. And this is just kind of combining it all together. This says it's positive and decreasing on the interval from -infinity to -1. And so here we did say it was increasing, and we also said it was concave down. So if we combine that together, that's what this is saying. Here and so we would have a local minimum at -1, and that local minimum is on the first derivative. So what that corresponds with is an inflection point at x equals -1, which, if we look back, is what we had said here as one of our inflection points. Okay, if we take the next interval, we said that that interval is positive and increasing. So that means it's going to be, the original function is going to be increasing and concave up. So if we look back at what we had said, we said that for that interval, it was part of this increasing and also the concave up, which corresponds with what we had analyzed it to be. The first derivative has a local maximum at x equals 1, so that translates into one of our inflection points, which we also identified that as one of our inflection points. And then if we move on to this next interval from 1 to 2, we said it's positive and decreasing, so that means the original function would be increasing and concave downward, which is what we had said. And then the last part of it from 2 to infinity, the first derivative is negative and decreasing, so the original function would be decreasing and concave downward. So our original function actually has a local maximum at x equals 2. Okay, so this is kind of putting it all together with the sketch, and you can kind of see in pieces here how it's all put together based on what the what our first derivative is doing and how that translates into these different segments of our graph that we looked at. So we looked at this part, and then we looked at this part here, and then this part here, and then on for the rest of it. So it kind of broke into 4 different intervals. Okay, if a company spends money on advertising, the hope is that sales will increase. Obviously, you want to get your money's worth for the advertising. Sales will increase rapidly at first, but then the rate of increase will begin to increase less rapidly. That is when the sales are at a maximum value and the function has a point of inflection. This point is called the point of diminishing returns. So you will, on some problems, be asked to find this point of diminishing returns, which is your inflection point. So an appliance store is selling dryers and decides to invest X thousand in advertising. It estimates that sales can be modeled by this particular function here. And this should be a 4. Okay, so we want to complete these statements here. So the first derivative has a maximum at x equals blank. So in order to find the maximum of the first derivative, not the maximum of the original function, but the maximum of the first derivative, we actually need to work with the second derivative. So our second derivative, well, first of all, take the first derivative. So that would be 3 times 3 is 9, x to the second, minus, we multiply 4 and 0.25, we're going to have 1x to the third, and then the derivative here would be 0. If we look at the second derivative, that's going to be 18x minus 3x squared. So if we want to see where it has a maximum, we've looked at finding our critical numbers. So that's going to be, I'm going to take out a 3x, and that's going to leave me with 6 minus x. So taking out a GCF of 3x. So I'm going to set each factor equal to 0. So I'm going to get 0, and I'm going to get 6. Okay, so we have 2 places that the first derivative has potentially a maximum or a minimum. So if we do our sign chart here, okay, it only goes, if we look at the domain, we can only look at from 0 to 9. So this part of our graph, and actually this part, doesn't even exist. And our other critical number we need to put on there is 6. So if I'm trying to find the maximum of the first derivative, I'm going to actually plug into the second derivative. Okay, so I'm going to put 5 into 5 would be a representative or a test point for this interval, so that would be positive and positive. This will be positive, and then if I put 7 in, that would be positive and negative, so that'll be a negative. So it means it's going to increase and then decrease, which means this is where my maximum is occurring at. So when x equals 6, that's when the first derivative has a maximum. So in other words, when the rate of change of sales reaches its maximum, then it actually has, then the original function has an inflection point at that point. So at x equals 6 is the inflection point. And so the point of diminishing returns is x equals 6. So in other words, after $6,000 in investments, you actually start having a decrease in the amount of sales that it's generating to continue putting money into the advertising. So the rate of change of sales begins to decrease when $6,000 is spent on advertising. Okay, so this is our original function that represents the sales. And this is our first derivative that represents the rate of change of the sales. So you can see how the maximum of our rate of change, it kind of peaks here. And that also corresponds with the inflection point of that first derivative because it goes from concave up to concave down.